Okie dokie. Somebody asked me a question on a homework problem. It's a little ahead of where we are. Chapter 10. In Chapter 10, as we started it. At the time of this recording, we got almost to this point. We were getting close. But in any event, Chapter 10 is, and Chapter 11 especially, but even Chapter 10, both of them equally, are going to still use our Bugs Bunny strategy. The only thing is, we're going to add in, oh, my tablet's getting funky. Hold on here and pause this. It worked. And I just noticed that I need to even update this a little more. The perpendicular, the parallel, and then the rotation, the torques. So parallel and perpendicular forces, torques don't have such a distinction, and may or may not. Not sum to zero. Okay, nice. So, and everything's the same. One difference though too is in addition to the torques, so we have a third line down here. And yeah, generally speaking, we'll set things up so that the perpendicular component equals 0, but there may be an exception. So here's a problem from the homework, and it's question 10.23, which is Chapter 10, homework number 7. So we're going to learn about a distributed free body diagram. So the weight of an object acts on its center of mass, and then in the normal, and normally we, forgive me the pun, we would draw the normal at the center of mass too, but because we have a torque involved, we need to make this so-called distributed free body diagram, and you'll see sometimes with a dotted line drawn here, and probably without this circular dotted line and the radius factor, and I just added them to make it a little easier. And so then we go to this. There's always two free body diagrams, and now we have the components, we have the real forces here, and we are going to define the plus directions as usual. And then we need to also define a plus direction for the rotation. And in this case, because it's rolling down the hill, we'll say that clockwise is the positive direction. Okay, so we have our, we see that we're going to be using W perpendicular and W parallel, so we might as well set this up. And it says here, slipping, with no slipping. So we have touched on this, and I remember. With no slipping, that means, oh no, what we did is we talked about it as a rigid body. But, and about a point on the rigid body. But it turns out that these, when we have an object rolling down an incline, for example, then if we say rolling without slipping, then that means that, of course, all the points on the object itself obey that. But now the relationship of the rolling object with the incline makes these usable. All right, so we'll get back to these. So, first of all, we see the perpendicular forces are at the usual culprits of the normal and the weight perpendicular. Excuse me, and they equal 0, so we can make this to say W cosine theta And then we see here, remember we're ultimately looking for mu sub s. So here, well, let's think this through. So there's a couple things we could do here. Let's write this all out. W sine theta minus mu sub s times the normal equals ma. And the idea is that even if it's rolling down the hill, the center of mass is going to travel in a straight line, and it's going to be accelerating. That's what this is, the ma parallel. And the friction is going to be a torque about the center, and the radius vector is the r vector, and they're perpendicular by definition, the way we set this up. So we have mu sub s times n times r equals, and then we look up for a sphere. It's 2/5 m r squared times alpha. And we notice too then that we want to get, so now we have unknowns, right? We want to get rid of them so we can reduce it to one unknown. And okay, first of all too, we can cancel that. And so we can substitute in an expression for alpha. And so alpha is going to equal a divided by little r here, but down here, of course, it'll become big R, equals 2/5 mr times a over r. So the r's cancel out. That's nice. And I'm betting that the masses are going to cancel out. Any time you deal with gravity, you expect that the masses are going to cancel out somehow, because remember that gravity has a magical property that it can supply the exact amount of force to give a constant acceleration. And even on an incline, it won't be 9.8 meters per second, but it'll still be constant. All right. So let's take a look at what we have here. And let's see if we can make some room. Unpause this for a moment. Okay, unpause. So we ended up here a moment ago. So the bottom one, we left with mu sub s times n times 2/5 ma. So I clean things up, and we see, so this is interesting. And so basically we have three equations, and we have mu sub s is unknown, or suppose w and n is unknown. We're given the angle, but we expect that the mass is going to disappear, and we don't know exactly what is the acceleration. So with three equations, it seems like we have, well, let's see, n and w and a and mu sub s, but w equals mg, so we'll see. In any event, I'm going to leave you here because now you have enough to solve it, because it's just algebra now. But see, basically, and I don't know if I said it before, but this is just a way of generating equations. We've done examples that were overdetermined, but this one is not. We need all three of those equations, it turns out, to get the answer. But in any event, I will get this up there now, and so you guys can have a look at it.